Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. And in this module we're trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? So within the second module, currently we are on the second topic, that is process address space, right? And here through a series of videos, we are trying to understand how does the memory appear to each process. So we have already studied that every process has its own associated process address space, which helps the process to organize its code and data in a proper way, right? And we have talked about this fact that this process address space is divided into four major sections, that is code, data, heap, and stack, right? And in the previous videos, we have talked about each of these sections individually in great detail. So now in this video, as we are nearing the end of this topic, right, I want to compare all the different sections and take a example where we are using all the three different sections. Till now, the examples that we have seen have focused on one particular section. So now let's combine all of the concepts that we have studied in this topic and see an example which will help us to see all of the sections in one big picture, right? So let's start this video and understand the difference between these, not the difference, but let's compare all of these different sections and get a complete picture of the process address space. So we started this topic by this basic picture, that is, this is a process, and every process has a set of addresses associated with it, which is called the process address space. And through this set of addresses, it is able to get a view of the physical memory, right? The processes are not allowed to access the physical address space directly. So instead of the physical address space, each of the process has its own virtual address space, right? And through its own set of addresses, it has to view the memory, right? So you can see this is the set of addresses going from 0 to some maximum value, and through this set of addresses it is able to view its code and data which is lying in the DRAM, right? So this address space has different sections, as we have already discussed: code, data, heap, and stack. And by now we know what each of these sections is for, right? So let's quickly recall what does each section do, right? So when you compile your source code, then you get a program, and your program is essentially a bundle of data and instructions. So the instructions of your program go into this code section, right? So this is the place where all the program instructions are stored, right? And apart from the code section, all the remaining sections store some kind of data, right? There could be different kinds of data, but none of them stores instructions. It's only the code section which has the instructions. So now let's talk about the other sections. As we know that the stack is used for the execution of function calls, right? Your program is a sequence of function calls, and the stack is reserved for this purpose only, right? And not only the execution of function calls, you can see stack from the perspective of a data storage, that is, it stores different types of data objects. For example, the local variables inside a function body, the function arguments, return addresses, all of this is stored onto the stack, right? Then we talked about the difference between static and dynamic memory allocation. So basically, when your program is executing, then there are two types of memory it accesses. One is one which is statically allocated. Basically, this is the kind of memory whose size remains fixed throughout the execution of the program, and that type of memory, as we know, is called static memory allocation, statically allocated memory. And we know that the other type of memory is dynamically allocated memory. In this case, the size of the memory that has been allocated, it can vary, it can grow, or it can shrink during the execution of the program, right? So we have studied that the data section contains several objects, for example, global variables, static variables, the constant values, and the common property of all of the objects that are stored on the data section is that they are allocated statically. That is, before the program starts execution, we know how much size each of these objects will take. So the size, the total amount of size, all of this is decided before the runtime. That is, at compile time, we know how much size each of these objects will take, right? So they are statically allocated. And finally, we talked about the heap in the previous section. So we know that the heap section is a pool of memory, right? It is a memory reserve that is reserved for the allocations that happen dynamically during the runtime, right? All of your dynamic memory allocations go to the are basically done from the heap section. So this was a brief review of what are the different concepts that we studied about each of the different sections in the process address space, right? So now we'll take a example where basically we are going to see all of these sections in action, right? So I haven't mentioned the code section, but that is kind of implicit. We are more concerned about how the different data sections, stack data and heap, come together. And let's take an example. Let's take a piece of code where we can see that we are using all of these three different sections, and let's get the whole picture, right? So this is the example that we have. So as you can see, this is a simple program written in C. Here, what we are doing, we are basically, let's go over the functions first of all. So there is an allocate function, right? And it takes an integer variable n, right? And it does a very simple thing. It allocates a memory buffer whose size is equal to that of n integers, right? You can see we are doing a malloc call, which is doing n into the size of int. So basically, it is reserving a memory buffer of size equivalent to that of n integers. Okay. Then let's see, here we have a global variable, and it is an array whose name is first and whose size is 100 bytes, right? So it's a global variable of 100 bytes, name is first. Then if you see, we have a variable called size, and we are asking the user to input this value size. It's an integer, right? And with the value of the size, we are calling the allocate function, and the memory buffer, the pointer to the memory buffer that is returned, that is stored in this second variable, right? So basically we are asking the user to enter a integer, and we will allocate that much amount of memory, right? If the user enters, let's say 200, then we are going to allocate the memory pool of 200 integers, right? And that buffer address will be stored in the second. Then there is some computation that we are not much interested in, and finally we are freeing up this second variable. So if you will carefully notice, here we are going to use all of the different sections: data, heap and stack. So let us see how. So basically, if you see here, here we have the process address space, right? So let me first of all initialize the data section, right? So in the data section, there is a global variable first, and it is an array of 100 bytes, right? So you can see, before the program starts running, this has been allocated. So this is statically allocated memory. We know the size, that is 100. Before the runtime, we know that this variable first, it is going to take 100 bytes, right? So not 100 bytes actually, this is 100 integers. So 400 bytes, let's assume that the size of the integer is 4. So 400 bytes, this we know before the program starts running, right? So here, as you can see, this is this allocation is done before the program starts. Now what will happen is that the main function will be called. The program has been launched. So here there is this size variable, right? This is an integer, and then this is second variable. This is a integer pointer, right? So you can see now the stack section is being used. We are using the stack section for the function calls. So we have the stack frame for the main function call, and you can see the local variables in this stack frame. So now the user will enter the value of size. Let's say the user has given the input as 50. So now we want to allocate a integer buffer whose size is equal to 50 integers. So let's say the size is 4. For each integer, we are allocating the buffer of 200 bytes, right? So now we'll call the allocate function. So we'll have this stack frame for this allocate function. Here you can see the parameter, the argument n is equals to 50, and the local variable buff, right? This is the variable which is local to this allocate function. This is the, here you can see it on the stack frame of the allocate function, right? So now we'll do the malloc, and this will allocate some, this will allocate some memory buffer on the heap section, right? So now if you carefully see, here we have the first variable, right? This is the first variable, and its size is 100 integers, right? Which is 400 bytes. Okay. And this memory buffer that we allocated on the heap, its size is 50 integers, that is 200 bytes, right? Half of the one, that is half of the second, this first variable. Okay. So now what will happen, you can now see that each of the three different sections, the code section is obviously being used to store the instructions, but as you can see, the data section stores this global variable. The heap section stores this dynamically allocated memory. So you can see, for the data section, we already knew that the size of the allocation would be 100 bytes before the program started running. 100 integers before this program started running. So we allocated it on the data section. For the second variable, we do not know the size before program starts running. Only when the user has input the given the input as 50, now we know how much memory we need. So at runtime, when the program is executing, at that moment we make a dynamic memory allocation on the heap, which is for 50 integers, right? So now this allocate function will return, and this address will be stored in the second variable, right? You can see this address 1f random address, right? This has been stored in the second variable. So you can see the allocate function has returned, the stack frame has been removed, and now the second variable points to this memory buffer in the heap section, right? So we have a memory buffer, you can say, or an array, you can say, of 100 integers on the data section, and another buffer of 50 integers on the heap section. The first one was allocated in a static way, the second one was allocated in a dynamic way. And now after doing some computation, we are about to end the program. We basically make a call to the free the variable second. So we are asking to free this memory buffer. So when that happens, this will be deallocated. So you can see the allocation, dynamic allocation, has to be done explicitly, and the same is true for deallocation. We have to make explicit calls for dynamic memory allocation and deallocation. And if we don't do this free, then there will be a memory leak. I have talked about this memory leak in the previous video also. So now the program is about to end. The main function will return, and when the main function returns, now the operating system is going to clear up the memory. It is going to destroy the address space, and during that time, this data section, that right, this object that was defined or automatically allocated at the starting of the execution, will be also deallocated, right? So this is how this program works. So now you can see how the three different all the sections of the process address space come together and help in the execution of the program. So this gives you a big picture, a complete picture of the working of all the different sections, right? So now we are going to briefly compare all of the different sections where we store data. So I'm going to compare the stack, data, and heap section at a high level. So let's talk about the purpose. So we have already talked about this several times. The stack section is the purpose of the stack section is to basically execute function calls and stores whatever data that is part of the function body, local variables, arguments, etc. Right? The data section, the purpose of the data section, it is to store the global variables, static variables, constant values, basically all of the variables whose size is known before the. So the common thing about all of these variables is that the size of these data objects is known before runtime, right? So these are statically allocated on the data section, right? And they live throughout the execution of the program, right? From the starting till the end, the objects on the data section remain allocated, right? And finally, there is a heap section. The purpose of the heap section is that the heap section is a pool of memory that is used for making dynamic memory allocation. Whenever you want to allocate something at runtime, then that allocation will be happening on the heap section, right? So now let's talk about the allocation, how memory is allocated in all of these three sections. Let's compare them. So you can see for the stack section, the memory size is determined during compile time, right? And the memory is automatically allocated at the beginning of function execution. So what does this mean? So this means that when we say memory size is determined during compile time, the layout of the stack frame, right? Where will be the local variables? How much size will be required for the local variables? The return addresses, the arguments, all of that layout is known at compile time, right? Because we do not have dynamic memory allocations on the stack section. Everything is the size of all the objects that are there on the stack section. It is known at compile time only. Though, so the layout is determined at the compile time. You can say it is statically allocated. The layout has been calculated at the compile time. But obviously the actual memory, right? The actual memory will be only allocated in the DRAM when the function call happens, right? Unless the function call, if the function is never called, then the memory will never be allocated for that function on the stack section. So there is a distinction that we need to understand. So if we recall an earlier video where I talked about detailed execution of the code, we saw how the assembly looks like and how do we create the stack frame, how do we destroy the stack frame. So in that example, you saw clearly how the layout of all the objects on the stack, the layout of the stack frame was tightly coupled with the assembly code, right? So during the code generation of the assembly, we know that okay, this much size will be required for the stack frame. So the addresses are calculated based on that. So everything is calculated, the size and the address is calculated, that then only the assembly is generated. So this is how the layout is decided. But a very important distinction is that finally only when the function is called, right, then only actual memory will be allocated in the physical memory, right? You can decide upon so when we say allocate, sometimes we mean deciding upon the fixing upon the size, but the allocate term is also used to when we actually allocate the memory. So here I want to draw a clear distinction that okay, the size of the stack frames, the layout of the stack frames, the addresses, everything is decided at the compile time. And even then it could be the case that that particular function is never called, so no actual memory will be allocated, and only when the function is called, then the memory will be allocated at the beginning of the function call, right? And let's quickly talk about the deallocation also. Basically when the function returns, then we have the just like when the function is called, the allocation is taken care of by the operating system. In the same way, when the function returns, the deallocation will be taken care of by the runtime or the operating system, right? So here you don't have to do anything. As a programmer, you just write your function. Allocating the memory and deallocating the memory is not your responsibility. It happens automatically. Now let's talk about the data section. So what is the data section saying? Memory size is determined during compile time and automatically allocated at the beginning of program execution. So the only difference between stack and data is that here we are saying it is allocated at the beginning of function execution, and here we are saying it is allocated at the beginning of program execution. So in both the cases, since objects on the stack section and the data section are not dynamically allocated, we know the size of the objects that will be on the data or stack section beforehand, right at the compile time. So everything, the layout, the size, the address, all of that is determined at the compile time, and only when the program starts executing, then we need to actually allocate the memory in the data section in the DRAM, right? So this is about the data section, how allocation happens. When the program starts running, the allocation happens as per the sizes that has been calculated at the compile time, right? And deallocation happens when your program basically terminates, right? At the end of program execution, your objects on the data section are automatically deallocated. Again, you don't have to do anything. Just like the stack section, you don't have to do anything for the data section. Whatever variables that you define, your static variables, global variables, constant values, everything is taken care of by the compiler, the runtime, the operating system. Everyone has a role to play. You don't have to do anything as a programmer. You just write your program, right? You write your function, or you declare your variables. Rest of the things will be taken care of by the compiler, runtime, or operating system. So you can see there is a very similar with the allocation and deallocation nature for stack and data is quite the same. The only difference is that on the stack, things happen uh, depending on whether the function was called. At the starting of the function call, the actual memory will be allocated, and when the function return, that memory will be deallocated. Whereas for the data section, it is like the lifetime of that data object is throughout the execution of the program. So allocation happens at the beginning of the program execution, and deallocation happens when the program terminates, right? Let's talk about the heap section finally. So when we talk about allocation and deallocation here, you as a programmer have to do explicitly. You have to do things explicitly, right? So here for allocation, you have to explicitly allocate using functions like malloc, right? And for deallocation, you have to do it again. You have to call functions like free at the runtime, right? So here basically, you as a programmer have to perform the allocation and deallocation explicitly. Unless you make that function call, you will not be allocated or deallocated the memory. So here, unlike the stack and the data section where the things happen automatically for you, here the it is the responsibility of the programmer. For allocation, they have to make calls to the runtime to request the memory for using appropriate function calls. Similarly, the deallocation will also be happening using the function calls. Here everything happens during the runtime, and it is done explicitly. In the case of the stack section and the data section, things are implicit. It is automatically taken care of, whereas in the heap section, the things have to be done explicitly. So this slide gives you a basic comparison of the different sections that are there on the process address space, right? So guys, this was it for this video. In this video, we took an example which summarized all the concepts that we learned through this topic, right? And we saw all the different sections in action through that example. And in the end we compare the different sections where the data is stored, how, what is the purpose, how is the allocation and deallocation happening in all of these different sections. So guys, this was it for this video. I hope by now you have a complete picture, a big picture of what are the different sections that are there on the process address space. So that's it for this video. Thank you very much for watching, and I'll see you in the next video. Thank you.